institute and we collaborate and make a protein on the surface, and then they study the student manipulated a lot of work on this cells, how behave on the pattern in the substrate, and this become a very standard reference for the people studying this area. And in the later, we make some pattern is physical structure in the surface, and we found that the cell also have a really strong behavior and shift to the to the area where there's an under layer, you have some space, and this is really understanding. And then later when we fabricate the soft pillar substrate, and that the different pillar, you know, today and then the people talk about transducer. That's the same area. That's I added this transponder for your pleasure, and then we make this one, and then we study the data behavior, which kind of substrate they like, and we find that not so hard, not so soft. They have a substrate about 10 kilopascal substrate is very good because it's the matching with this the stiffness. That's really great. We make this some kind of structure cell, and then put the cell on this substrate, and then once develop somehow, and then they start to begin beating, and we remove this this stem cell, and then the cell will make a vibration together, and very homogeneous to a very large area. This is some early work. And today, and then after we also did a lot of work, and even now we are trying to mimic the cellular microenvironment by creating the mostly is the so-called baseline membrane. We created this genetic nanofibers, just mono layer, so it's 100 nanometer thick, and then we just make a cell assembly with the proteins for base membrane, and we find that this is very wonderful technique. They created with 100 nanometer thick protein network is physically and biochemically really looks like the biological basal membrane. That's what we developed some gadget for me to introduce this one to create the blood channel and also the others, and we trying to try different things, neurons, cardiac, liver, lung, and different things. That's okay. That's make us some confident that this is a very good thing, and then at the same time we try to commercialize this one to provide researchers for facilitating their work. Okay, today I want to concentrate on the CDC. The CDC is from the very beginning young born parents, laboratory who was in the institute. Here in institute, we went to see him. But he said, okay, that's challenging. He said, can you during 10 minutes select just one cancer cell from the 10 million cells? That's a way. Later we just make some physical devices and try to answer this challenge, and later that's what attracted our interest. I mean, in Paris, there's a great place for many people to interact with each other, and then we talk is that's bring us into this area very efficiently. This is people you are all know that the CTC what's the mean, and what is the technique that is diagnostic in parallel. We have CTTMA and electrons, and among many techniques, it seems that the membrane technique is the most simple, and technically, since I'm come from the physical side, and then we have some fabrication technique, we try to focus on this one and bring this to the age of this application. Since the first generation we work out is based on the hypothesis that CGC is larger than other blood cells, and then if we make a membrane with the holes slightly smaller than the CTCs, and that a blood cell can feed out, and then CTC can be calculated and isolated. And then that time, some people or the doctor even you can ask us that the question is how to make the blood cell pass very rapidly. But from physical point of view, that equation is the differential job, the pressure job across the membrane proportional to this air. Air is the thickness of the membrane. From physical point of view, if we reduce this moment to 0, we will get less pressure job with the same speed of flow. That's will be helpful for the cells. And to reduce the physical point of view, if you make this conical angle, if this angle becomes very small and that's become the air, you can consider it 0. Okay, so that's we can largely reduce the transmembrane drop and then the capture cell. We rapidly with PDMS work out on paper, and let's make some use in the French television David 1 and report our result and with some collaboration with comments on this, and then rapidly we make some prototype with this kind of device is plastic because we want to make this is useful in clinic. We make this device. That's a tumor, and that's one 2 plastic layer, and just sandwich all this membrane, and then put the blood in this cylinder, and then we apply pressure, and then we can get this capture isolation. So this is very simple technique, and you can make later on immunochemistry and the fish and the chemistry to analyze. Okay, and then rapidly we develop this multi-channel system, and then also fabricate this membrane with the so-called nano-imprint technique massively. Everything becomes commercial industrialized, and then we also develop some software. This part is in China, in Paris, we go before the research. So now this machine is used in China, and maybe 700 cases per month, and is in the hospital. And then we are hoping that we can go further. Okay. So quickly we move to the second generation devices. The second generation, we, as I said, we suppose that the blood cell, including white blood cell, are smaller than CTC, but this is definitely true. There's some blood cells, that size is larger than the CTCs. So suppose you have only one per person with large cells, they will block these holes of the membrane. That's in the left side, you see the many cells blocked, and then maybe CTC among them stay there. And then this causes a problem because you have it's how the pressure drop rapidly, and then you have a loss of your CTC, and then you have to increase the pressure. I will explain later. And then rapidly we design this type of membrane. Make this membrane, the Lambo membrane is more than 1 million holes per centimeter square. And then in that case, with 5 microliter blood, and we can still have a large number of open holes. That's we hopefully we see that we can probably reach the low stress. The cells, since there's no pressure drop, and then we hopefully these cells will be more of the variable, and then we can do some more interesting work. From physical hand, and we are dealing with flow. Flow dynamics is very described by nervous equation. And then you can see if you reduce this equation, you become this equation. This is on the left is pressure drop, and then it is proportional viscosity eta. Q is the speed of flow, and N is the number of that opening hole. D is the size of the hole, and then you have H is the thickness of the hole. So I asked my student, please just make an experiment and to test, evaluate the influence of each parameters. That's what we call the schematic study. It's very typical in French. Okay, and then we will find that there's a very simple calculation. You will see this equation is reversely to the this number of n, because the size of the hole we cannot change it too much. And the n increases when the number becomes less than 80%, and this pressure increase, this pressure drop increase rapidly, and then lesser cells will be no more stable in the membrane. They will go away. And then we experiment rapidly, we detect this when this is reversed, and you can see the behavior is exactly like the theoretical prediction. Okay, the fabrication of this membrane, and then we have to evaluate the capture efficiency and also the different things. And then I go faster. You see the fabrication is very easy. We just using the lithography technique is not so hard, and then make a mold, PMS mold, and then make reverse the replication by this UV resist, and after you can have this kind of two-level structure. In the bottom you have this filtration field, and the other part is supporting frame. This is the frame. You can see this structure is very that's the fabricated, and the cylinder make a different type of different thickness, different hole size, different the pore number, etc. And then we can very easily reach 1 micron thickness and very solidly stay for the filtration, and that's give us great chance to develop other things. And then this is the membrane characteristic, and this is we can try to do with hydrophilic molecules, and then to control their reactivity. Compared to the first generation, you can see this is this diameter we can make a more relaxing, and then for the whole numbers, the porosity and then changing. Due to that, the decrease of thickness of the pitch side in the holes become also largely decreased. That's the kind of increase largely the porosity of the membrane. Okay, and then the device to study is very simple, as I showed in the first, in the very beginning. The membrane is here M, and then you have this plastic layer, and then you have two plastic layers, and then one in the medium is elastic layer, and we can put this the blood in one say in the cylinder, and then in the bottom channel we can use other medium, and then you can see that we can control with this cylinder for P1 and P2. We can control the relative pressure, and because P2 is to feed the cylinder to keep the same level, so that the cylinder pressure drop, and then to study the effect. The device is also very similar with the prototype in the laboratory. So this formula, then I come back to this formula because we can see here is the more complex, because we have this coupling equation, Navier-Stokes equation, and then we have a hydraulic pressure because it depends on the height of this blood sample, and we have also different parameters. Anyway, if you make a simple calculation, you will get the very easy prediction and corresponding to the parameters of membrane we fabricate. And then next, we will notice rising the student very glad every time they graduate is exactly as theoretical slide. This is the figures, the experiment cover by varying the flow velocity, by varying the diameter of pore size, and by varying the thickness of membrane. This knowing that this is without the cells, we can also very rich information which also fit that Navier-Stokes equation. And this is another if we let the sample in the cement, the level will go down, and suddenly when the level will go down to very small and very small pressure, because there's no liquid. But if we keep this liquid on the same level in the cylinder, again, this is I come back again this location if you have idea so we measure it. Then we added also this so-called three-dimensional dispersed. The cells come home, they can disperse in the homogeneous in the whole cell area. Otherwise, they just have some zone cells are less populated. This is correlated with simulation. And with the cells, and that's also very easy to carry out. We select some cell and we call it SPO KV3 and HEPG2 and other, and then we have other type of cell we call background cells, and then we can add a very small number of tumor cell and with a large huge number of background cells, and then we can study this how influence the cell number in this pressure drop. And then it's the same thing as case without cell. And then this is also we can say this, we can play with the pressure. If you capture these cells and then you suddenly increase the increase the speed, and then that means you increase the pressure drop, and there's some cells are lost, but not very efficient. Since most of the holes are opened, and that's I will talk later on other technique to use this filament. And this on the right side is a slice on this kind of membrane. It's just side by side and highly populated. Most of the more course are background cells. CTC are just amount maybe 1 million we can detect. And the variability also largely increased, as I told, and the pressure drop, transmembrane pressure drop is very small. We keep the minimized, so the cell will be not damaged. We compare with a small membrane, with also with a large number of background cell and with a small background cell. Large background, that means most of the holes are blocked, and this in this case the cells, the transmembrane pressure will be increased, and then the captured CTC will be lost, and this is why we need to increase the number of CTC, and that's why we test different cells to prove to optimize the diameter 7 and thickness 7 is the best to optimize everything. Okay, that's I think I also like to talk about more and on this on the CTC effort. This we, as I said, that we can recapture cells, and some people want to recover this capture cells. We can induce this pressure from the bottom side, and hopefully this cells will be CTC capture cell will flush away. That's indeed we observe this before and after flush. Talk with this image we can see, and we have this also quantitative assessment. And as the most hole are opened on this side, and this flush effect become less efficient. If you want to really flush away all the capture cell, we can use another technique, means that we introduce some microparticles in the bottom channel. So these particles will block the hole. When the most block hole are achieved, and then the remaining hydrodynamic force pressure will be upset the cell where they have not lived, and this is just like a resistance. Actually, this is very efficient. We just a small piece of work, and hopefully it becomes useful. And this release cell, we test the viability is also perfect because there's not much pressure applied. Come back because capture CTC is one thing, and then we also need to capture them, and to capture them we make further, and with this kind the membrane, add the nanofiber substrate or the protein content substrate. We also did some double layer is structure. With that same technique, what we talk to my student just make some small holes. Now this is not the organ examiner frame, just the holes, and then we can cut a CTC, and then by counting this substrate with protein, they can also form the very similar protein network, and the cells will be alive very easily. And hopefully we are also counting some protein or chemical molecule make a small network. In that way, we hope we can also in the same device capture exosome and also ctDNA, but unfortunately, through the finished their work, and we just left this technique. Maybe later when we can use it, because in the same time, in the same devices, we can in the upper stage we put this CTC culture membrane. In the bottom, we can add another membrane with this molecular filtration membrane with functionalized molecule. Hopefully, we can in the same device we have ctDNA and the CTC. This is the protein, the culture. There's no this protein counting, and it becomes more efficient. And then in the same time, we develop modeling technique. We want to form a tumor. The ultimate goal is to use CTC to form spherical tumors. This is challenging, and then we just started to develop some technique. This is the technique of culture this tumor. So this is not from CTC, but a normal tumor cell, and they are stay in this high temperature from the membrane, because this is on the left. The bottom thickness is very small, 5 micron, and the tumor cell can very easily form a spheroid, and then we can use this transmembrane impedance very nicely measure the behavior of this cell. For instance, if you take the time when they make a growth, and both capacitance and the resistance increase with time, that's correlated with the size increase. This is also physically understandable. And with the same time, this is the same technique we try to develop this long-term dynamic culture. This is a device, CGC probably in this small tumors, and in the outside we just culture, we have a culture medium, they just make the rocking. So the free flow just in the bottom channel, and the CTC are there, and we try to calculate different things. Everything works like we expected, and also we are trying to add some drugs, and we find that under this dynamic culture condition, and everything become different, because the cells are more more compact, and then they are more resistant to the drugs. That means for the drug assays, everything should be more realistic on the on the dynamic flow condition. And then we are trying to make the same device. One side is the culture device, on another on the downstream we have the capture device, and then we can form this loop. And you see that we can apply drugs on the left device culture cell. That's where we have the tumor, and on the left, if some cell under action of drug, and they can flow on the second, on the downstream device captured, and then we will analyze what type of the cells, how they react with this of the drugs, etc. So this can also reversely make different tumor models. And we just gradually test this device, and also just prove what the principle is easy. But to develop something really useful for clinical application, there's no way to go, because we need a more tighter connection with hospital people. And in the same device, we now move to the generation of large organ model. Okay, that's why we use this same device, but make this rocking of centrifugal tube, and this is a flexible You have a very freedom. You can change the angle, stop by, and control everything very easily. Not like the normal the shaking machine. This kind you can control time and etc. And then we get a very nice and very large is numinized organic structure. That is going on. And then for the I think I finished my work in by means and conclusion mark. We see on this state work, and we see that the high porosity membrane, minimum percentage is very necessary for CTC detection. That means from our point of the most early CTC captured by working with membrane and not very reliable because their number really small. People say that okay, 50,000 is a huge number, but it's not nothing to worry with 1 million holes per semester. We will make an explanation. And also pressure control filtration is also necessary because that's for the real cell detection is very sensitive. And clinical, even though we make, for example, following the clinical principle for the publication, but the real application will be most systematic study. By the way, the study technique will not improve because we find this technique just the protein, this biomarkers are too expensive, not very, not really rich enough to satisfy our studies. And also for the CTC capture for culture, for CTC with other cells, really expect we are currently doing this things in the laboratory, and also advanced tissue tumor model are really expected for really understand how individual happened. So the number of questions I just by preparing this PPT, I see this PPT, this technique is used for really for individual study diagnosis. But in principle, this CTC, this technique also for the individual dialysis because the number is large. We know that we have no most blood cell can pass very easily, and then hopefully we can test this later on. And then the one question is that I mentioned maybe at the same time we can detect exosome and CTC analysis. And also for clinical, this is our dream, and also really task for everyone because in the clinical for the patient, we cannot, we don't know how to use drug. Doctors will even say that you try this one, this does not move, change another one. But in this way, and the people, the patient get so-called drug resistance is not is very bad. So we have to take clinical samples and test individual, and then if something is really patient, then apply to the patient. So this is so logically actually the hospital way is not logical. But technically speaking, it's quite possible. We test some rapid new devices and new devices to get a protocol. And then how to develop more realistic model. That's better dish. I mean, in the CTC, they cannot just alone to form the tumor, and we need some fibroblasts, maybe immunocells, and the different cells, and put it together. We are moved to this direction, really to hopefully get more realistic model. And also there's some technical question, how many cells involved in tumor metastasis, we don't know. We need to, even if we culture and what is the culture, the larger cells, what type, and what is their status decision. This is very easy question to answer, but we have no chance to answer it. And the development of new markers is a big challenge, but I think it is surely possible. If we culture these cells, and we will have a chance to develop these markers. Otherwise, if you cannot capture them together, you just use available markers to track something there, and it's not sufficient. And the performance, fortunately, performance of image detecting increase rapidly, and this also AI assisted analysis also become very popular, and together they give us a very great chance to improve I chose it very much. And I just said this, we can put the three together, three chip together. One is for culture, another is almost neurons, something to make this kind of both the best, and the next one is the culture set together. And then I think the general approach, we have some commercial product. We are just preparing now is almost video, and then to hope people can use it very simple to deal with this very hot and fantastic subject in the future there. And then for the clinical application, we use this so-called just one people for sample detection. That's the introduction of the sample. Clinical sample should be limited in minutes, and also the remaining things should be really very easy and automatized. And also the tumor connections should be minimized, not make effort on this gadget. And we have to move to the real problem, biological problem. Okay, that's the work of mostly the student of Noor Houye and Tanya Hatton is also the first one beginning in 2014, and Jim is the biologist. The new is my colleague in Japan, which called have a lot of stem cells, and other people are also involved. I like to thank them, and also thank you for your attention. I think the time is over. I stop here. Thank you.
Thank you very much. Okay, I don't know how it works, but basically we have microphones, so we can maybe. Do you hear me, Yong?
Can you close the microphone, because I heard not very so clearly.
Can you hear me better now?
Yeah, yes.
Okay. So maybe I can handle. So is there any questions?
How do you get the second coefficient of viscosity?
How do you
get the second coefficient of viscosity? The Navier-Stokes equation he has given. So there is another term for, apart from eta, there was another term.
I'm not sure. Okay. I got the question, but okay, maybe you can move the micro here. And okay, please. So it's kind of micro.
So the Navier-Stokes equation you have shown, there are viscosity coefficient eta, and there was another term. So how do you assess that value?
The viscosity you can change it. You can add some polymers and change the viscosity of the medium. Yes, you can very easily tune the viscosity. And the speed you can judge the synergy parameter. And the other parameters you can just by the fabrication different type of members.